Greetings and welcome to a new video about electric circuits. This will be our example number 3 about maximum power transfer. In this case we will look at the situation using the theorem of Thevenin and Norton combined. So that will be a complete discussion about the maximum power transfer using the previous discussion about Thevenin and Norton's theorem. Of course, we will work out everything step by step in our calculations and also verify these in SPICE simulations. So let's look at our circuit. This circuit is rather complicated as shown here, so that's actually a challenging example here to illustrate the concept in great detail. We have 4 sources, VA, VB, IP and IQ, so 2 DC voltage sources, 2 DC current sources. So these are the values. And we have 5 resistors actually, R1, R2, R3, and R4 and R5. Those are given. And also we have a resistor load RL connected here between these 2 nodes at the output. What we want is calculate the required load resistance RL, that is unknown, to transfer the maximum power to the load from actually all these sources. And in this case, the polarities are given here, so the VL and IL, and we have also the X and Y denoted here for future calculations. So how to do this? What can we do in these situations? So we know, let's first start with that, we know we need to convert this after several steps in a circuit, equivalent circuit like that. This is the Thevenin voltage. And there's a Thevenin resistance, and this part is called the Thevenin equivalent circuit. And that is then connected to, between the nodes X and Y here, exact same 2 nodes, to the load resistance we don't know yet. In order to have the maximum power transfer, we need to have RL, which is the load resistance, equal to R Thevenin. So once we know R Thevenin, we can say that must be the load resistance. Now we can combine the theory from the Thevenin and the Norton's theorem combination using source transformation, and this is really powerful. I have actually read a lot of circuits, books about electric circuits. This discussion is not really clearly explained in all books, so there are books that do a very good job in other topics, but it is kind of skipped or maybe not really explained in great detail. I would like to do that. That's actually also the purpose of this video. You have actually source transformation between the Thevenin's theorem, which says this is a circuit, the equivalent circuit, and its Thevenin voltage and Thevenin resistance. These 2 values we need to determine. But you have also the Norton's theorem, which has a current source and a Norton resistance. And also between the 2 nodes X and Y. But there is a relationship between these 2 circuits. We can go from left to right and from right to left. And that is really handy when you have a lot of DC sources or AC sources, doesn't matter, but a lot of sources, independent sources, if you want to convert them. Now we can say the Thevenin resistance, RTH, is equal to the Norton resistance. That is always the case. And the Norton current, by using Ohm's law, is equal to the Thevenin voltage divided by the Thevenin resistance. So once you know these 2, you can calculate directly the Norton's Norton current. Or if you know the Norton current and also the Norton resistance, you can multiply these 2 to get to the Thevenin voltage. That is also possible. Now we will use these 2 circuits, let's say the templates, in order to convert our circuit directly to an equivalent circuit. And that can be done really nicely. We have a couple of steps, of course, to go, but you can see that in action in steps. So let's go now to the actual circuit and then move on for the calculation. Now using source transformation, combining the Thevenin and Norton's theorem. So first step is convert, in this case, or recognize actually there is a Thevenin equivalent circuit, or Thevenin circuit for short. And that is actually the VA and R1. You can see there is a series combination of these 2. So that's a voltage source in series resistor, which is a Thevenin circuit. That can be converted to the Norton, like that. So we have now VA is converted to a current source by dividing by the R1. So it's actually shown here. So we make a current source. Remember, the polarity is plus and minus. Your current must go up, your current source. And your resistor here will be then parallel to that source you have generated. That is the new source. And this is VA over R1. What is VA? 20. What is R1? 10. So you know this is 2 amps. Now this part is now a Norton equivalent circuit or Norton circuit. And this part here is the Thevenin circuit. So we have actually converted this to that. Why do we do this? The reason for doing that is the following. You see now the R1 and R2 in parallel, and that can be combined easily by using the formulas for two resistors in parallel. So the step 2 is, or the next step, I should say, is combine now R1 and R2 together. So let's call this RC. And R1 and R2 parallel is this formula, R1 times R2 over R1 plus R2. Now we know the values, 10 and 40 for R1 and R2 respectively. So we calculate it and you get exactly 8 ohms. So we have it, and that means this circuit now can be converted in that circuit. So we have an RC here, still this 2 amps, and now this circuit is generated. What do you see here? What do you recognize? Now the following is also visible. This circuit with the current source in parallel with this resistor RC is a Norton equivalent circuit. That can be also, again, transformed back to a Thevenin equivalent circuit. Why we should do that? Then we can get this RC in series with the R3 and we can combine them again, and this will be then a voltage, of course. So the next step is then the following. Convert this VA over R1 source and this RC from Norton circuit into a Thevenin circuit. This is 2 amps, and that must be now multiplied by this RC, which is 8, and you will get then 16 volts. So this part is Norton, and you will now get this circuit. So you multiply actually this with the RC. That's actually shown here. And now we get the RC in series with this new voltage source. And that is 16 volts. And this is still the same. This is still 8 ohms. So that 8 ohms for RC. Now it is in series with R3. That is, of course, nice to have, because now we have an RC in series with R3, and that can be easily calculated by using series resistor formula. So this is the Thevenin part. Now moving on, let's collect them. This is the RC we need later. This is now 8 ohms. This is 57. So it means combine now for the third step RC and R3. And that's just RD. I just call it RD. So that means RD is RC plus R3. 8 plus 57 will give you 65. So I have now 65 volts here. I also have 65 ohms, and I have 16 volts, and I also have VB here. We know the following. If you have two voltage sources in series, you can combine them to make one voltage source. If you have two current sources in parallel, you can combine them to make one current source. That's also valid. So this is 65 ohms, and now we can say combine now this 16 volts with a VB of 10 volts, and that is 26 volts in total. Why? Because they have the same polarity. You can see at this node I get VB plus 16. And now the circuit becomes this. So you can see it already getting simpler from the original circuit compared to that. So RD is still here. That is 65 ohms. Now we get 26 volts, and the rest is still the same. Now we can again do the same business. So we started with converting this Thevenin format to a Norton circuit. This is again a Thevenin circuit. So we can say this 26 volts and this RD of 65 ohms. I can also convert that using, again, conversion from Thevenin to Norton circuit. Again, 26 volts over RD. RD we know, 26 volts over RD. That is this current. So you can calculate that as 0.4 amps or 400 milliamps. The RD is exact same as before, that is 65 ohms, but that is now in parallel to this new current source. Now we have a nice thing here, and the reason for doing that, the motivation for doing that is you get here a current in parallel with a resistor, and this current and that current source, now you see that IP and this current source are in parallel, so we can again merge them together to get one current source. The actual reason for all doing these steps is to merge all these sources together to get one source only and one resistor only. That is the final goal we have already presented in the beginning, the Thevenin equivalent circuit. So now I will combine these two, so the IP and the 0.4 amps source we're going up. But now we need to be careful because this source is going down, which is now a combination of 0.4 amps and 6 amps. This is going up, but this is going down. So effectively, I go down by 5.6 amps. That is very important here because you need to really be careful with the signs. So the circuit then becomes, you go down, so from the top now to the ground, by 5.6 amps. And the RD is still there. Now we get again in the circuit, much simpler. Again, we simplify actually for each step. You get simpler and simpler circuit, and this is now 5.6 amps, and the rest of the components are as shown. Now we can convert again this Norton circuit to Thevenin circuit. So that's again the conversion back to the Thevenin. So 5.6 amps going down, that is really important. With this VRD, you get actually the following. So 5.6 amps times RD, which is 65, and you will calculate 364 volts. But now you need to be very careful. You can see also that in the source, it is plus up and minus up and plus down. Why? Because the current flow here is going from top to ground. So I need to also place that in the priority for the voltage source. VD will be now in series with this voltage source, and now will be then also in series with RD, and that is also fine. Now we can combine them. So the next step will be then this 65 and this 75 of R4 can be combined to get a new resistor, just one resistor. So we can say, let's call it RE. So I go actually from RC, RD, and RE. So I will just produce a new resistor name. That will be just 65 plus 75 will be get 140 ohms. So the circuit now becomes this. You can see it is still nice, and it is also much simpler than the original circuit. Now we have the RE in series with that voltage source of 364 volts. Okay, let's move on, and we know we still need to convert, because if this current source wasn't there, I can just combine these two and then say this is the Thevenin resistance, this is the Thevenin voltage, and I'm done. But I need still merge this and combine that with the source here, so we need to move on. That means again a Thevenin equivalent circuit, combine that or transform that actually to a Norton equivalent circuit by doing exact same as before. So we do 364 over RE. That's actually shown here. That will give you 2.6 amps. Again, the direction going down for the arrow for this current source. RE will be parallel to that current source. That's actually shown here. And this IQ and the R5 and the load are still in the same position. Now we have a Norton equivalent circuit here. And I see and now two current sources are parallel, IQ and 2.6 amps. But IQ was 4 amps given here. That goes up, and I go down by 2.6 amps. So effectively I go up by 1.4 amps. So we can also use that. So we can say, let's now combine 2.6 amps and 4 amps for IQ. I go up effectively by 1.4 amps. If this was, for example, 2.6 amps, and then I have actually currents of 0 ohms, 0 amps there. So that's actually a very special case. Still the RE there, and there's an R5 and R load. Now we have a Norton equivalent circuit. Now we can convert that back to a Thevenin equivalent. Why? Then we have RE in series with R5, and then we can combine that easily. So let's do that. Step 11 already, so 1.4 amps and RE from Norton to Thevenin circuit conversion. That's shown here. So what we do, we use again Ohm's law, current times resistor. 1.4 times RE. RE was 140, so we will get 196 volts. Again, the polarity goes up, so that means minus and plus. And RE will be now placed in series with that source, and it will be also in series with R5. Now RE is 140 and R5 is 105. So we can say, let's now combine these two resistors and make that, let's say, RF. We can say RF is equal to RE plus R5. RE 140, R5 is 105, so you will get 245 ohms. That's RF. Now we are actually almost done. So we have our resistor here and we have our voltage source here. And that's also what we wanted. So just a voltage source in series with a resistor. So let's then collect everything we have here. So we need to calculate the maximum power transfer. Still, that was the question. And this is the circuit we got finally. But we know these are the two nodes between the load. And this was the general circuit for the Thevenin equivalent circuit, which is connected to the load. Again, X and Y. Thevenin equivalent circuit. Now, Thevenin voltage, looking actually to this circuit and also our circuit in the final step, is that Thevenin voltage is 196 volts and Thevenin resistance must be then 245. That's just actually this one. So RL now must be calculated by using the maximum power transfer theorem. It says the RL must be equal to R Thevenin in order to get the maximum power transformed from the source to the load between the node X and Y. So it means quite easily R Thevenin is RL. That means RL is equal to 245 ohms. And that is really the answer for this question. Okay. Now let's also look at the simulations, because we have now this circuit and prepared actually our Thevenin voltage, Thevenin resistance, and also from that load resistance. Let's also look at the simulations. This is the simulation circuit I have prepared. You can see the original circuit elements, so the voltage VA, VB, R1, R2, R3, R4, R5, and also the IQ and IP for the current sources. This is, you can see the current goes down and current goes up here. And already we'll place the resistor for the load of 245 ohms. Now, let's check what we measure here. You can see it measures 400 milliamps here through this resistor. And there's also voltage of 98 volts across this resistor or load. And those are shown here. So it's highlighted in red here. We can also say, let's go directly and use a circuit for Thevenin, so Thevenin equivalent circuit, and then RL connected. This is also similar to the original circuit. Only difference is that we only have two components here connected to the load. Now we have here, if I now do the analysis here also, I get directly 89 volts, and also the current of 400 milliamps. So it is exact same as we have seen here. So how do we know actually that we get the maximum power transfer for this circuit? We can show you that also in the simulator. So I will also go to the simulator and show you the results there and how to generate these tables. You can also make a plot there and see and sweep actually the value of RL and see for yourself that this is really the value 245 ohms that you really require to get the maximum power from all these sources between the node X and Y. So let me now go to the SPICE simulator and show you there the more details. So we continue with our simulation discussion. This is the actual simulator. So we have the circuit. This is the circuit. We can see the voltage source VA, VB, and also the resistors, and also our load we have chosen. I would like to demonstrate also using this simulator that the current and also the voltage what we have determined is correct, but also more importantly, that was the actual question, that this is indeed the maximum power here for this specific value of the load resistance, because that was the question. We didn't know the load resistance. We have calculated it must be 245 ohms, but let's also verify this in the simulator. So first do analysis, DC analysis, and just check the voltage here. So we can go here and then click on this with a pen. You can see directly the 98 volts and 400 milliamps. That's just a verification of the two values. But let's also sweep the value of this component. So we can do the following. We can say, I would like to, let me just remove this. This is not really interesting, that node Y. This value here is set here as 245, but let's also determine that using a plot. So we can go to analysis, DC analysis, and do the DC transfer characteristics. Now I would like to know what the value of that RL is, which produces the maximum power. So we can sweep here, that is the input, several values. So you can say I would like to sweep the current. If you're interested, for example, in this voltage, maybe you can also sweep that. So you can sweep one parameter at a time. So I will choose, of course, RL. And these are the number of points. So to make the plot more accurate, so I have chosen for, let's say, the 30,000 points is sufficient for this discussion. Start with a 0 ohms and go all the way to, let's say, 5 or 600. So let's go to 600 ohms. This is just the beginning and the end of your sweep parameter. If I run this, you will get this. Of course, I also need another thing, so I forgot that actually, so let me also do that. So let me also insert here a current arrow. So I do that by going to meters and then current arrow, and also show you that this is IL, the load. Let me also use an actual voltmeter to really see that this is also a voltmeter. So this is the voltmeter, must be of course between the two nodes of the load, and I also call it VL for my load. So I have now two measurements for this load. This is of course set to this value, but it doesn't matter for the sweep. So during the sweep, the simulator doesn't care about this value. This is just for fun, let's say. But let's do again DC transfer characteristics. Again, we run this. So let's do that. Okay, we get some values. Let me make this larger, the plot, like that. Okay, let me bring this circuit to the right side, left side. So to reserve some space here. Okay. It is going. Okay, now let's now do separate curves. It's already something which I will again show you. So I will remove this. So remove this also. So you can see two plots. The IL, that's a green, and then the VL, which is given in, let's say, dark red. This one. So you can see also the sweeping. So if I now, let's say, do 7 ticks, then I will go in 100 ohms, so going to some specific value, and then show you the voltage increase and also the current decrease. That is of course normal. If you increase your load resistance, your current goes down, your voltage will go up. And this is the input resistance, but it is actually the load resistance. So let me also show you that in the plot also. What I want to show you is the generation of the power curve. So we go to post-processing, and I go more, and I also use these two values. So I say IL must be times, so this is the operation, times, that's the X, VL, and I call that, let's say, load power. Okay, and I will create that. It's now created. So there's actually new functions. So I times V is just the power. So we get it. Now we have it here. So let me give that a new color. Let me make it blue. What do you see? Now, this is the max, this is the power. So you can see it multiplies actually each point and you get the curve. So green times red will be blue. Load power, PL. And then we have actually sort of a peak here, and then it goes down again. So it gets an optimum. So let me then check that. So we can use the cursor here, place it on this. So there you can see the A. You can go up, 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 and now go down. So you can actually just go left or right with this cursor with your mouse and see where the maximum is. But what you can do easily is go here. So let me again show you that. Go here, click on it, right mouse click, jump to global max. What do you see? this X is 245 ohms actually, because that was the load resistance, and it produces 39.2 watts. This is actually a confirmation that this is indeed the load resistance we need for maximum power transfer. This is, again, remember, the actual circuit, not a Thevenin equivalent circuit. So if we don't know anything about the circuit, we can again simulate this and so verify this for ourselves by multiplying the voltage of the load and also the current of the load, because that is the P load. Now this is what we have, and if I, of course, let me do that, let me make the full screen here. You can also label this and make this larger. Let me say that 24 is, I think, enough. You can see at that value of the load resistance, you get 400 milliamps, we have also calculated, and at the same value of that load resistance you get 98 volts, also we have calculated. So we can see those are also verified from the simulation discussion. Alright guys, this was for this example about maximum power transfer in a circuit where we have a lot of the sources with a lot of also resistors for the load. And what we have done here is a combination of the Thevenin's theorem and also the Norton's theorem combined together to use the source transformation. And that will be very helpful for a circuit like that where you have a lot of components and elements. If you have any questions about these exercises, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.